Welcome to the second lecture of our series about statistics. This lecture will be about measurement errors generally, and I will also introduce statistical estimators. Imagine a very simple experiment in this example. You want to measure optical density OD600 of your bacterial culture. So you do your experiment, you put an aliquot of your bacterial solution dilution in this cuvette and and measure optical density. The instrument will give you a result. In this particular case, is 0.37. It's an OD600, and there is an associated uncertainty with this result, which is called a reading error. If we do the same experiment multiple times, that is, put different aliquots in each of the cuvette and do individual measurements, then we are going to find a mean of all these measurements. We get a result. Let's say the result is 0.42. The uncertainty of this result is called a sampling error. These two are examples of measurement errors, and that's the topic of the first part of the talk. First of all, there is a very general division of errors into systematic and random errors. Systematic errors are essentially your mistakes, something that happens in the lab, something went wrong. For example, incorrect instrument calibration, changing experimental conditions, pipetting errors. The other type of error is a random error, and they are there because statistic sucks and just we have these errors. Will be reading errors, sampling errors, and related to intrinsic variability. The difference between these two types of errors is illustrated in this. Systematic errors are responsible for a systematic shift of all the results from the real, true, accurate value. Random errors cause the scatter of these points around the center. Systematic errors can be reduced and eliminated in good experiments. You can't eliminate random errors. You have to live with them. You can estimate and reduce random error by taking multiple measurements, which means you need replicates. Every experiment has to be done in replicates because they allow you to estimate uncertainty or error of your result. The simplest error is reading error, and it's related to the reading device, something like a ruler or a gauge or a measuring cylinder, where you have a scale. And typically it's assumed that the reading error is about plus minus half of the smallest division, like shown here. So with a ruler, if you measure something with a ruler, you would say 23 plus minus 0.5 millimeters, because this is a reading error. You have to be careful with digital instruments that can sometimes give readings with much better accuracy than the real accuracy of the instrument. For example, this particular thermometer shown here gives you a reading with 1 decimal place here. So you could assume that the accuracy of this is 0.1 of a degree. However, if you read instruction manual for this thermometer, it will tell you that actual accuracy is plus minus 0.5 of a degree. Reading error does not take into account biological variability, which is usually much larger than any reading error. Have a look at this simple example. Let's say we want to determine the strength of oxalic acid in a sample using titration. That means we add a basic solution to this and then observe the liquid until it becomes neutral. We can use sodium hydroxide solution for this. And this experiment has multiple stages, and each of the stages can add a little bit of an uncertainty in the final result? Well, first of all, there will be an uncertainty in a volume of the acid sample because it's measured down to a certain accuracy. There will be uncertainty in judgment at which point acid is neutralized, and it's just down to you, the experimenter. You observe it and you decide when it's neutralized. And also uncertainties in volume of sodium hydroxide solution used, and the accuracy of sodium hydroxide concentration, which in turn depends on the weight of the solid NaOH dissolved and volume of water added. You can make a very, very simple approximation of how measured values behave here in this experiment. Imagine that this red dot represents the true measured value of the strength of the acid. But when you do experiment, each of these steps will add some error. It will get essentially add a random number to the result. And it could be either a positive or negative random error, depending what you do. And in a very, very simple model of this, you can assume that with every step of the experiment, you add a small error of the same size, either plus or minus. And you immediately see what it leads to. If you remember a binomial distribution from the previous talk, you will remember then tossing a coin multiple times, or tossing several coins, will lead to a binomial distribution of the result, which will be, for example, the number of heads. The results where you have negative error, negative error, negative error repeated multiple times will be less likely. The same results with positive error every time, but there will be mixed results somewhere in the middle. And the final distribution of this, if you repeat your experiment multiple times, is a binomial distribution, and it will approximate normal distribution when the n sample size is large enough. The final result is a random variable with about roughly normal distribution. So I want you to remember from here that measurement errors in most cases are normally distributed. A special case which we can discuss separately is a counting error, which is a pure statistical error from Poisson distribution. Imagine another experiment where we do dilution plating of bacteria. This is a result from one experiment. We have 10 colonies. And if you remember from Poisson distribution, it has this very interesting property that the standard deviation of a distribution is the square root of the mean. And we can use this standard deviation as an error estimate to obtain the standard error of a count. We simply take the square root of a number, of a count, and the standard error would be about 3, which means you can finally write down your result if you have 10 counts with error bar on it. That will be 10 plus minus 3. Let's do a Gedanken experiment. The term Gedanken experiment is a German Latin term, part German, part Latin. It was first used by Hans Christian Ørsted in, I believe, 1812. Ørsted was a physicist, Danish physicist and chemist. He discovered that electric currents create magnetic fields. And then it was popularized, the term Gedanken experiment was popularized by Albert Einstein, who used it to perform experiments that are not possible to do in real life. He, for example, considered trains moving at the speed very close to the speed of light. So we are doing Gedanken experiment here, something you can't do in the lab, but you can easily simulate in a computer. And this is what I'm doing here. I measure counts from 10,000 plates, and these counts will be distributed according to the Poisson distribution. And the first 16 plates from this thought experiment are shown here. A result is a dot, so the count of 10, this is count of 16, this is count of 15. And the error bar here is the plus minus square root of the measurement, as shown here. If you continue this experiment and do it 10,000 times, you can then build a distribution of the results. This is the distribution of 10,000 counts like this. And this is actually a Poisson distribution, counting distribution. It's got the mean, and the mean value is represented here. And there is also a standard deviation of the entire distribution, which is the square root of the mean. When we do one particular experiment, we are trying to estimate the parameter of this distribution, mu. So CI, each count from different experiments, each of them is an estimator of the population mean, mu. Or SI, the square root of the count, is an estimator of this width of this entire distribution. As you can see, from the particular experiment, particular instance, the count can be either lower or higher than the true mean here. And the error, like this error, can be larger than this or can be smaller than this. So they are not perfect. They don't give you the final answer of what the mean and standard deviation of this distribution are. They give you an approximation. This is what is called an estimator. I will talk about this in a moment in more details. But since we know how to use errors on counting distribution, we can have a look at this example. In October 2013, our local journal, The Courier, published an article with a title, Dundee is Murder Capital of Scotland. And in this article, they didn't publish a nice table like this, but there were some numbers scattered along the article. Number of murders in year 2012, 2013. And they also mentioned the number of murders or murder rate per 100,000 inhabitants. And according to this table, well, Dundee has the highest number, highest rate, 4.1, followed by Glasgow with 3.2 per 100,000 inhabitants. Now, these are numbers, but there are no errors here. There are no uncertainties, so we really don't know how different these numbers are. So let's try using our knowledge about counting distribution and calculate uncertainties of these counts. I just consider Dundee and Glasgow, just for simplicity at this point. And to calculate errors of the rate, I will start with calculating errors of count, of the raw count, because this is the uncertain number. This is the count that follows the Poisson distribution. That means from year to year, this number will be different. On one year, it could be 6, on another could be 4, another year it could be 10, and so on. So it follows a Poisson distribution, and the error related with the Poisson distribution, as you know, is the square root of the count. So the error on this number, or I will call it count C with index D, is 2.5. An error on the Glasgow count is 4.4. If you have an error and you just simply scale your number, and this is scaling, this is just dividing by the population and multiplying by 100,000. So it's a scaling by a constant number. And errors scale the same way as numbers. Or in other words, fractional errors are the same. If there is a, let's say, 10% error on this number, there will be a 10% error here. Let us calculate these fractional errors. It's very simple. I take error and divide it by the number. This is for Dundee. So the fractional error on Dundee number count is 41%. It's quite high. It's very uncertain number. And in case of Glasgow, it's about 23%. And now we can apply them to the murder rate and multiply the rate by the fractional error by this 41% and 23% here. And we get these errors of the rate. It's always better to look at your data. And this is when you plot the murder rate and its error. This is the standard error of the murder rate. And as you can see, standard error of Glasgow murder rate actually is entire inside the error of Dundee. There is no difference between them. If you perform a statistical test, a Fisher's test, I will talk about it later, you will see that there is absolutely no difference. So the statement that Dundee is a murder capital of Scotland is completely unfounded. It's based on misunderstanding data and statistics. We can have a look at all data, also for Aberdeen and Edinburgh. These data were published in this article. And indeed, the comparison with Dundee, maybe indeed Edinburgh has much significantly lower murder rate. But even then, if you can see here, the actual number of murders is 2. So it's such a low count that it's hardly, we could hardly trust these results. Let's summarize what we have learned so far. Random measurement errors are expected to be normally distributed, which means in terms of repeated experiments. If you repeat your experiment again and again and again and collect all the results and build a distribution of your results, this will be approximately normally distributed in most cases. Some errors can be estimated directly, like a reading error from a scale or gauge, and counting errors, they are kind of a special case. Other uncertainties require replicates. You need a sample of your measurements, and that introduces sampling error. And to talk about sampling error, we have to first talk about population and sample. These are concepts which are nicked from social sciences, where population is quite literally a population, a group of people, for example, in a specific country. This is actually a nice pre-COVID picture. You can't see this anymore. And from this population, you make a selection. You have a sample, which is just a few individuals out of the entire population. In biological experiments, you usually have a sample of something, but the population and sample, these terms are not always literal. Population can be actually quite an abstract term. Now we have to differentiate between a biological meaning of a sample and statistical meaning of a sample. Because in biology, often a sample is a specimen, e.g. a cell culture you want to analyze. In statistics, sample is a set of numbers, set of measurements. If you have 5 biological specimens, let's say each there is a solution in a tube, you do some sort of quantification, you process these samples and you measure something, for example, optical density, you will end up with a set of numbers. And this is our statistical sample. This is what we are going to call a sample, a set of numbers, a set of measurements. A sample is simply a subset of a population. And population could be very abstract. Population could be a set of all possible measurements. When you have, for example, a bacterial culture and you measure optical density of this, then population would be a set of all possible measurements, perhaps even infinite set. This is an abstract term. This is not real. There are true unknown parameters of a population, and I will use Greek letters to denote them. Mu is the population mean. Sigma is the population standard deviation. Now, a statistical estimator describes a sample. So if we have a sample of size n from this population, we can then calculate various things. We can calculate m, the mean. We can calculate standard deviation, SD. So I'm using different notation for the sample and different notation for the population. The estimators, this is a statistical estimators, these are known. This is something that you measure. The population parameters are unknown. They are ideal true values hidden somewhere in nature, and we are trying to discover them. And in statistical estimator approximates the corresponding parameter in the population. And this is where we get to sampling error or sampling uncertainty. You can imagine population as all possible measurements. So And if you plot a distribution of these measurements, this is the true unknown distribution showing biological variability. This is not statistical noise. This is actual variability from subject to subject, from measurement to measurement. It will probably, apart from biological variability, it will also include some technical variability because your protocol introduces errors as well. So this is the full uncertainty, full variability of what we are going to measure. Now, when you do experiment, you select a small sample, for example, 5 biological replicates from this population. And the sampling variability means that if you repeat this again, you will get different results. For example, this is experiment 1. You have sample of 5 measurements here. There are 5 numbers. And this vertical line represents the mean. This is what we are interested in. If you repeat entire experiment, the 5 biological replicates again, you get different values and a different mean. If you repeat it again, you will get different values and again, different mean. This represents or demonstrates sampling variability. Your sample is random and your result will be random as well. And from sample to sample, it will change. A quick question, you can consider this for a second. When you have a dilution plating experiment and you have 10 colonies here, what is the sample size here? Well, I hope you said 1, because this is just one measurement, one number. The value of this measurement is 10, but despite having 10 colonies, the sample size is only 1. It's time to talk in more details about statistical estimators. This is a quote from Des McHale, who is a professor of mathematics at University College Cork in Ireland. Apparently, he was a very funny man. So he said the average human has 1 breast and 1 testicle. Okay, what is a statistical estimator? Let's go back in time. This is a drawing or picture from from a book published in 1575, a very long time ago, and the title is Right and Lawful Root. Root is a unit of measure which is equal to 16 feet, and it's from the book Geometry by Jakob Köbel, published in Frankfurt. And with this illustration comes a text, and it says, "Stand at the door of a church on Sunday and bid 16 men to stop, tall ones and small ones, as they happen to pass out when the service is finished. Then make them put their left feet one behind the other, and the length thus obtained shall be a right and lawful root to measure and survey the land, and the 16th part of it shall be the right and lawful foot." Köbel did something quite amazing over 400 years ago. Well, he introduced random sampling from a population. He said, select some random people, essentially, that are leaving the church. He specifically required a representative sample. He said, tall ones and small ones. Do not select only tall people because it will affect your result. He defined a standardized unit of measure, which is a root and also a foot, based on this random sample. He used 16 replicates to minimize random error, and he calculated an estimator, the sample mean. Imagine you have a sample of 7 mice, and you measure the body weight. The results are shown here. So this is our sample. There are 7 measurements, 7 numbers. And from this sample, we can find the mean, median, standard deviation, standard error, interquartile range, and many other values. All of these are statistical estimators. A statistical estimator describes the sample. The entire sample, lots of numbers in the sample, can be reduced to just one number. This is the statistical estimator. And the statistical estimator, as I said before, it approximates the population parameter, as shown in this simple diagram. Imagine we have a sample of 30 measurements. Now we have body mass of a mouse here. And from this, you can find the mean and standard deviation. These are estimators from our sample. On the left, there are population parameters. There is true unknown population mean and true unknown population standard deviation. And capital M estimates mu, and capital SD, standard deviation, estimates sigma. This is our best shot at guessing these true unknown values. Very briefly, before we go to other estimators, mean and median, they should be quite obvious to you how they are defined. Just a quick comment that median is more appropriate for skewed distributions with outliers, perhaps. So on the right, there is a sample of several measurements with two of them being much larger. They are potentially some outliers. And the median of this result is still here, while the mean is dragged up by these two outliers. And this is the case of a symmetric distribution where mean and median are very similar. So median, on the other hand, is a better estimate of the central value than the median. And mean, the statistical tests based on the mean, like a t-test, are more powerful than non-parametric tests. Essentially, if your data are symmetric and doesn't contain outliers, you should use the mean. Median is only useful for things that have lots of outliers. Standard deviation is a measure of spread of data points, and it's illustrated in this figure. Imagine you have 12 measurements, so this is measurement number 1, 2, and so on, from 12 mice. This is again a body mass. The sample mean is represented here by the dashed line, and the points show measurements. The gray bar shows the deviation from the mean. And the idea to find the spread or define somehow the spread of data around the mean is as follows. First, you calculate the mean. You need to know this. And then you find deviations from the mean, these gray lines. Then you have to get rid of negative signs. If you simply add all these deviations, some of them are positive, some of them are negative, and they will just cancel out and won't tell you about the spread of the mean. When you get rid of negative signs, you somehow combine them together. There are several ways of doing this. You can, for example, use absolute value and find the mean of these bars. This will be called a mean absolute deviation, or it's not very often used. What is most often used is a standard deviation. And you can find in literature two different definitions of standard deviations. I will mark them as SD with index n and index n minus 1. What we do here is, as I said, we calculate the mean, it's capital M. We find deviations from the mean, xi minus m, it's a deviation of data point I from the mean. We get rid of negative signs by taking a square of this and then combine them together. I will calculate the mean and then take a square root again to go back to original units. If your mass is in grams, this quantity will be in grams squared. So you take a square root to go back to original units. And the other possibility is instead of dividing this by n, you divide it by n minus 1. There are several reasons why this is actually better. One is related to the number of degrees of freedom. I will mention this a bit later. Another is that this estimator of variance, so squared standard deviation, is better estimator of true variance than this one. That's one of the main reasons we tend to use this one, the second one. Now, the major sort of a main topic of today's talk is standard error of the mean. In the previous talk, I introduced sampling distribution. And sampling distribution is something like that. You take a population of, let's say, mice. We assume a normal distribution. The mean body weight is 20 grams and standard deviation of this distribution is 5 grams. This is our population. This is a distribution of individual weights of each mouse. Now we built sampling distribution by taking a random sample of 5 mice from this distribution and calculating its mean. And then we show the sampling distribution of the mean. So this is the distribution of all sample means. You see that these both distributions look well similar in a way that both are probably normal, and indeed they are normal, but this one is narrower. They both are centered around 20, which is the mean of this distribution, but this one has a different standard deviation. And from theory, we can show that standard deviation of this sampling distribution is the original standard deviation sigma divided by the square root of n, where n is the sample size. You can imagine this distribution to be built as a result of multiple experiments. So this distribution here is only hypothetical. In real life, I don't know this. I can only simulate it in a computer and show something about its properties. So in this hypothetical unreal experiment, we have 100,000 samples of 5 mice. The first 8 samples of this experiment are shown here. And there are measurements, 5 measurements, and the vertical line represents the mean. So we have mean, 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 lots of means from each sample. We kind of collapse them together to this plot and they build a distribution of these means. And from theory, we know that the standard deviation, the width of this distribution is sigma divided by square root of n. In this particular case is 2.2 grams. This is the width of this distribution. In a real experiment, which is marked here, which is our sample number 2, we have just 5 mice. We measure the body mass. There are 5 numbers, and we can find standard error. And what we do, and it's often done in statistics, is a trick that when we have some equation for a population value parameter and we don't know the result, we can replace one of the population parameters, sigma, by its estimator. And the estimator of population sigma is our standard deviation. So we take this formula and find what is called standard error of the mean, and it's 2.7 grams. And standard error of the mean is an estimator of the width of the sampling distribution. It's an approximation of sigma m. And if we do this experiment with a different number of mice, let's say now one sample is 30 mice, then we'll see that the means are much closer around the true mean and this distribution is narrower. And in real experiment, the standard error would be also smaller. So this is sigma is 0.9 of a gram. And our standard error, which is an approximation of this, is 0.87. This is the comparison of these two thought experiments. And now I specifically show where the mean is, where the standard error is, which is the black arrow bar, and standard deviation, which is a gray arrow bar. Standard deviation represents spread of data and doesn't depend on the sample size. And you can see that both on the left and on the right, all these standard errors are approximately the same, at least similar. However, standard errors here, the black ones, are are much smaller than in the left, because each standard error here tries to approximate this number, the true unknown number, this width of the distribution, and each standard error here tries to approximate this distribution. So what it is, and just to stress this again, the narrower the distribution, the sampling distribution of the mean, it tells us that in repeated experiments, the means are closer and closer towards the real true unknown mean. So the width of this distribution is the uncertainty of the mean, and standard error approximates this number. So standard error tells us how accurate the mean is. And this is the comparison of standard deviation and standard error. These are equations. As I said, standard deviation measures dispersion in the sample, and standard error is actually the error of the mean. Standard deviation estimates the true standard deviation in the population, the sigma, while standard error estimates the width or standard deviation of a distribution of sample means. This is the difference. And this does not depend on the sample size, and standard error gets smaller with increasing sample size. Very briefly at the end, I just need to mention a correlation coefficient. I won't discuss and go into any details of this formal definition, which you can see here. Just a brief mention, because we are going to discuss errors or uncertainties of correlation coefficient later. This is a measure of correlation between two samples, so of the same size. So if you have a sample x1, x2 up to xn, and y1, y2 up to yn, and you plot x versus y, if these things are correlated or they depend strongly on each other, as in this figure, the correlation coefficient is high, it's close to 1. If they are uncorrelated, you just see a random blob, random distribution of points. The correlation coefficient is close to 0. And if they are anti-correlated, so when x increases, y decreases, the correlation coefficient is close to -1. So R, the correlation coefficient, is a number between -1 and 1. And a word of caution, correlation does not mean causation. There is this brilliant website here, you can see where it is, which which picks up completely spurious distributions between various quantities. This one shows a correlation between divorce rate in Maine in the United States and per capita consumption of margarine, because there's absolutely no reason for them to be correlated. This is a fluke. And this gives us a very high correlation coefficient of 0.993. But now this is not real, obviously. So remember, the fact that your data are correlated doesn't mean there is a causal link between them. And to finish, a summary of statistical estimators I mentioned today. Some of them measure central point of data, like the mean or the median. There are other things like geometric or harmonic mean, mode, trimmed mean, and many others. The measure of dispersion of data is variance, which is just a square of standard deviation. There is standard error, mean deviation, range, interquartile range, and mean difference, and others as well. There are estimators that I didn't mention, which tell you something about symmetry of your data, which is skewness and kurtosis, and dependence, like Pearson's correlation coefficient, rank correlation, distance, and many others. Thank you very much. This is the end of the talk. You can find handouts and videos of all our lectures at this web address. Thank you.